In this video, we look at how power series can be used to express functions. In Unit 3 of the Mathematics A-Level course, you will have seen that the functions of the form 1 plus x to the power alpha can be written as a power series in x using a generalization of the binomial expansion. And we obtained the fact that 1 plus x to the alpha can be written as 1 plus alpha times x plus alpha times alpha minus 1 over 2 factorial x squared plus alpha times alpha minus 1 times alpha minus 2 over 3 factorial x cubed, and so on. But that this series was only valid if x lay between minus 1 and 1. What we're now going to do is we're going to investigate whether we can get similar expansions for other functions. In particular, we're going to start off looking at e to the x. So we're going to suppose that we can write e to the x as a series of the form a0 plus a1x plus a2x squared plus a3x cubed, etc. And we're going to try and deduce what the values of a0, a1, a2 and so on must be. Well, it seems sensible to say that if we're going to have equation 1 holding, it should certainly be true when x equals 0. And if I put x equals 0 in, the left hand side is e to the nothing, which is 1. The right hand side is simply a0. So this suggests straight away that a0 should be equal to 1. If we now differentiate equation 1, we're going to obtain the derivative of e to the x, which is e to the x on the left hand side, and then the right hand side is going to become a1 plus 2a2x plus 3a3x squared plus 4a4x cubed, etc. And if we substitute x equals 0 again into equation 2, we now obtain that the fact that the left hand side is 1 and the right hand side is just a1. So we've got a1 must equal 1. Differentiating both sides of equation 2 now, derivative of e to the x is e to the x, and the right hand side now becomes 2a2 plus 6a3x plus 12a4x squared plus 20a5x cubed, etc. Putting x equals 0 into equation 3 gives me 1 equals 2a2. In other words, a2 must equal a half. You won't be surprised now that we're going to differentiate both sides of equation 3 to obtain e to the x equals 6a3 plus 24a4x, etc. Substituting x equals 0 into equation 4, we've now got 1 equals 6a3. In other words, a3 must equal 1/6. So there on the top left of the screen is what we've just done. So what we're saying now is that the first few terms in the power series for e to the x are 1 plus x plus a half x squared plus a 6x cubed, and that is the Maclaurin polynomial of degree 3 for the function e to the x. And if we look at the graph of y equals e to the x, together with the graph of y equals 1 plus x plus a half x squared plus a 6x cubed, then we can see that for values of x which are close to 0, there is very little difference between the value of e to the x and the value of 1 plus x squared over 2 plus x cubed over 6. In other words, we can say that for small values of x, e to the x is very close to 1 plus x plus a half x squared plus a 6x cubed. So let's continue the process of finding the power series for e to the x. So if we differentiate each side of equation 4, we're going to obtain e to the x is 24a4 plus 120a5x, etc. Putting x equals 0, we get 1 must equal 24a4. In other words, a4 must be 1/24. Differentiating now both sides of equation 5, I'm going to get e to the x is 120a5 plus 720a6x, etc. Substituting x equals 0 into equation 6, we've now got 1 is 120 times a5. In other words, a5 is 1 over 120. And going through the process once more, differentiate both sides of equation 6. We get e to the x is 728a6 plus a whole lot of other terms. Substituting x equals 0 into that, I'm going to get 1 is 720 times a6. In other words, a6 is 1/720th. So, we've now got the Maclaurin polynomial of degree 6 for e to the x, which is 1 plus x plus a half x squared plus a 6x cubed plus a 24th x to the 4 plus 1/120th x to the 5 plus 1/720th x to the 6. And if we draw a graph for e to the x and the graph of this Maclaurin polynomial of degree 6 for e to the x, we get this. And in this case, we can see that the Maclaurin polynomial and the original function are in very good agreement for values of x lying between -2 and 2. So, we've got e to the x is approximately 1 plus x plus a half x squared plus a 6x cubed plus a 24th x to the 4 plus 1/120th x to the 5 plus 1/720th of x to the 6 for values of x satisfying -2 is less than x, which is less than 2. Now, notice that 2 is the same thing as 2 factorial, 6 is the same thing as 3 factorial, 24 is the same thing as 4 factorial, 120 is the same thing as 5 factorial, and 720 is the same thing as 6 factorial. So we can rewrite this as e to the x is approximately 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4 plus 1 over 5 factorial x to the 5 plus 1 over 6 factorial x to the 6. If we were to continue the process of differentiating and then putting x equals 0, we could of course get more terms in the power series, and the next 3 terms would simply be 1 over 7 factorial x to the 7 plus 1 over 8 factorial x to the 8 plus 1 over 9 factorial x to the 9. And again, we could have a look at the original function together with the graph of the Maclaurin polynomial of degree 9, and we can see that in this case we seem to have very good agreement, certainly between x equals -3 and x equals +3. And this suggests that provided we consider a large enough number of terms in the series, then we can write e to the x equals 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed all the way along to plus 1 over 9 factorial x to the 9, and general term in the series looks like 1 over n factorial x to the n, and that this will be valid for any value of x. So, the Maclaurin series for e to the x is this series that we've just been looking at. 1 plus x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the 4. General term is 1 over r factorial x to the r. Using GeoGebra to compare the graph of e to the x with the first few terms of the Maclaurin series has suggested that this result is going to be valid for all values of x. Now what we want to try and do at this stage is generalize the process that we've just used to find the Maclaurin series of e to the x to get a formula for the Maclaurin series of an arbitrary function f of x. So we're going to suppose that f of x is equal to a0 plus a1 times x plus a2 times x squared plus a3 times x cubed, and has a general term of the form an times x to the n. And we're going to use our process as before of putting x equals 0 and differentiating, putting x equals 0 and differentiating, etc. So starting off, if we substitute x equals 0 into equation 1, we get f of 0 must equal a0. Now differentiating equation 1, the left-hand side becomes f dash x, the right-hand side becomes a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus 5a4x to the 4, etc. up to an x to the n minus 1, and so on. Putting x equals 0 at this stage tells me, or gives me, f dash 0 must be the value of a1. If we now differentiate both sides of equation 2, we're going to get f double dash x, or the second derivative of f, is 2a2 plus 6a3x plus 12a4x squared, etc. Putting x equals 0 gives me f double dash 0, or the second derivative of f at 0, is 2a2. In other words, a2 is 1/2 of f double dash 0. If we move on, differentiate both sides of equation 3, put x equals 0, we're going to get the third derivative of f at 0 must equal 6a3. In other words, a3 is 1/6 of the third derivative of f at 0, or f triple dash 0. So we've now got the first four terms in the Maclaurin series for f of x are f of 0 plus f dash 0 times x plus f double dash 0 divided by 2 factorial times x squared plus f triple dash 0 divided by 3 factorial times x cubed. Now we can obviously carry on the process of differentiating, and then putting x equals 0, differentiate and then put x equals 0 to get further terms in the power series. And if we did this, we would obtain f of 0 plus f dash 0 times x plus f double dash 0 divided by 2 factorial x squared plus the value of the third derivative of f at 0 divided by 3 factorial times by x cubed, plus the value of the fourth derivative of f at 0 divided by 4 factorial times by x to the 4, plus the value of the fifth derivative of f at 0 divided by 5 factorial multiplied by x to the 5, and so on, with the general term being the value of the nth derivative of f at 0 divided by n factorial times by x to the n. Notice that we're using this notation of f to the n of x as a shorthand for the nth derivative of f evaluated at x. Now this is the Maclaurin series for the function f of x, and the statement that f of x equals the Maclaurin series may be true for all values of x, but may only be true for an interval of values of x around x equals 0. It all depends on the function that we're considering. So let's have a look at a couple of examples. We're going to first of all look at the Maclaurin series for cos x, and we'll use a graph drawing package, in this case GeoGebra. You may be able to do it on a graphical calculator to investigate its range of validity. So if we've got f of x is cos x, then we need, to get the Maclaurin series, we need some of the derivatives of f of x. The first derivative is minus sine x, and when x equals 0, the first derivative has a 0 value. The second derivative is minus cos x. When we put x equals 0, we get f double dash 0 is equal to minus 1. Differentiate again, we get the third derivative of f is sine x. When we put x equals 0, we get the third derivative of f at 0 is 0. If I differentiate again, I've got the fourth derivative of f of x is cos x. So when I put x equals 0, I've got the fourth derivative of f at 0 is 1. And we can keep going, just keep differentiating through and obtaining the results. Okay, now we know that the Maclaurin series for a general function f of x is given by the expression f of 0 plus f dash 0 times x plus f double dash 0 over 2 factorial x squared, etc. So in this case, the Maclaurin series for cos x is going to be 1 plus 0 times x minus 1 over 2 factorial times by x squared plus 0 times x cubed plus 1 over 4 factorial times by x to the 4 and so on. So we're ending up with 1 minus 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4 minus 1 over 6 factorial x to the 6 plus 1 over 8 factorial x to the 8 minus 1 over 10 factorial x to the 10. So, looking at the graph of f of x equals cos x, which is the red curve here, and the graph of g of x, which is 1 minus 1 over 2 factorial x squared plus 1 over 4 x to the 4, which is the Maclaurin polynomial of degree 4 for cos x, we can see that there's very good agreement between minus pi by 2 and pi by 2. If we instead look at the Maclaurin polynomial of degree 10 for cos x and compare it with the original graph, we can say that in this case there's certainly very good agreement between minus pi and pi, certainly, and it's a little bit further than that, possibly minus 5 pi by 4 up to 5 pi by 4. And what this is suggesting to us is that the Maclaurin series for cos x is actually a very good approximation for cos x, and that the series will be valid for all values of x provided we take enough terms in the series. So as an exercise now, to finish this video off, what I'd like you to try and do is first of all find the Maclaurin series for sin x, and then use a graph drawing package to investigate for what values the Maclaurin series is valid, and then to do the same thing for the function which is the natural logarithm of 1 plus x. In the next video, we're going to have a look at how power series can be used for more complicated functions.